Last month, you'll remember that we talked about sort of an introduction to filters. And I gave you an overview of what they are, what they do, and how they're made. So tonight I'm going to talk to you about how to choose the right filter for your application, whether it's observing the planets or the moon, or if you're trying to get around the issues with light pollution where you live. I also had a lot of interest in the last meeting in special filters, so I am working on part 3 of the presentation, and it should be ready in a month or two. So let's start by looking at solar system observing. And what I mean by that is looking mostly at the moon and the planets. Now, if you recall, in part 1, I presented the idea that filters are used to darken some features in order to make other ones easier to see. That is exactly the case when you use filters to enhance your view of planets and the moon. Now, in most cases, the filters you're going to use to achieve this are color filters. And this is a selection of color filters that are used for solar system imaging and observing that I'll talk a little bit about later. So how do you decide what filter of these, and there are many more available to choose from, how do you choose which one you want to use? Well, unfortunately, that is a very subjective question. There's a lot of trial and error involved, and at the end of the day, it all boils down to personal preference. So, as I mentioned, these are some common filters that you would use for planetary observing. And I broke them up by basic color group. And you'll also notice that they're all identified with a number. Now, if you recall last week, I talked about this fellow Frederick Ratton, an English inventor. So these numbers are the Ratton numbers. So these are numbers out of his catalog of filters. So the blue filters, you can see they're all essentially wide bandpass filters with their center frequency centered somewhere around kind of 430 to 450 nanometers. Green filters are also bandpass filters, but their center wavelength is more around the 520 to 540 range. The yellow to orange filters down here at the bottom, they are all essentially high-pass filters. I don't know if you remember, I talked about the different kinds of filters there last month. So they're all essentially the same type of filter. They just have a different cutoff wavelength, starting down around 460 and going all the way up into say 620 or 640. And above that are near-infrared filters, but you can't see those with your naked eye. You can't see infrared with the naked eye. And finally, the plot in the lower right, they're all some more unusual color filters that are still used for planetary work. So any filter that has a magenta or purple color, they are essentially green blocking filters. Like, oops, wrong button, sorry. Try to reverse the laser pointer is a little finicky. So you see how there's a dip here centered around the green wavelengths, around 500 to 550. So anything purple has that characteristic. And filters that are light brown or light orange, they're very similar to a normal orange filter, like over here, but they have additional emission in the blue spectrum down here. As I mentioned earlier, there's a lot of trial and error required to decide what the best color filter to use on each target is. Many amateurs have already done this work for us and have reported their findings in various media such as books and websites. But when you combine all of these different sources like I've done here in this table, you'll find that it creates a pretty extensive list. In my opinion, it's making things a little bit too complicated. Having to deal with so many filters, it's kind of like a big science experiment. You know, you have to have your little bucket out there with all the different colors and have to have a look-up table and figure out, okay, what I'm looking at now, I've got to change to this color. So that, to me, that's too much work. So I did my own little experiment, and I looked at many of these different filter types to figure out, you know, what actually do you see when you use these different filters. And for the most part, I was disappointed because the improvement you see is really subtle and very subjective. Now, in all the testing I did, there were some filter types that stood out. The first one is magenta filters. And there's a couple of examples here. The CC20M, that stands for Color Correction 20 Magenta. That's a newer type of color filter that Kodak makes. But they're all sort of in the same family as the Raton filters. And then the 47 and the 30, those are Raton numbers. So these filters actually do a pretty good job at increasing contrast on Mars and Jupiter. They help to kind of separate different colors in the planet. So I found them to be quite useful. Another class of filters that were very handy were red filters. Number 23, number 20, 25, and 29 are the most common ones that you'll find. Now, I found them useful on the Moon and Mars. It really helped to improve the contrast on the surface, and it also helped to settle down the atmospheric seeing. Now, the only problem with these filters is, with the naked eye, they are pretty dark. And I'll talk a little bit more about that later. Another pair of filters that I found pretty useful were light tan to light brown colored filters. 81B and 85 are good examples of those. I found that they increase contrast on Jupiter and Saturn. And then finally, for looking at the Moon or Venus, very bright objects, using a variable polarizing filter or a neutral density filter I found to be very helpful. Cutting the light intensity down just a little bit helped the eye to adjust and see more detail. So, this is my short list, a little bit better than the previous table. But if you want something even simpler, and you're looking for a one-size-fits-all kind of filter, there is something out there. There is something called a moon and sky glow filter, which is what I would class as a special filter. It's not really a color filter. And I'll talk a little bit more about that in part 3. It is, by the way, the only filter that I use today whenever I do solar system observing or imaging. So, at this point, I think it should be pretty clear to everyone that when you add a filter, what you're doing is removing the light or blocking the light of something you don't want to see. And what I haven't really talked about, though, is the fact that by blocking some light, you're making the whole image darker. And this can be an issue because for some apertures of scope, you won't be able to use some filters because the view will be too dark. So, in the table here on the right, I have listed pretty much all of the color filters that you're going to encounter doing amateur astronomy. I've even included a number of color correction filters, blues and reds and greens. I've also included in this table my calculation of what the luminous transmissivity of each of those filters are. I don't know if you remember from last month, I talked about luminous transmissivity. It's sort of an average brightness or average blocking of the filter to tell you how dark it is. And I've given you these numbers for two different situations. One is when your eyes are light adapted, or for photopic, in this column here, or if your eyes are dark adapted, so scotopic. And there is a pretty significant difference. The spectral response of our eyes changes quite a bit, whether they're light or dark adapted. So what this table and graph allow you to do is decide whether or not a filter is going to work for your aperture of telescope. So if we take as an example, the number 23A red, this is a light red filter. And if we were going to look at something that's fairly bright, like say the moon or Venus, most likely our eyes are going to be light adapted when we're looking at the moon or Venus because they're so bright. So if you take the percent LT value of 27 and you go over here, 27, come up, it's about 100 millimeters, or about a 4-inch telescope. So that filter probably is going to work okay as long as your telescope is bigger than 4 inches. Now, if you're looking at a darker object, like a planet, one of the planets, Mars, Jupiter, Saturn, quite a bit dimmer, your eyes are not going to be fully adapted to the light. It's going to be somewhere between photopic and scotopic. For sake of argument, let's just assume that your eyes are dark adapted when you're looking at the planets. So the percent LT for that number 23 filter is only 1.8%. So if we go way down here to 1.8%, you're going to need a telescope that's on the order of 8 inches in diameter or larger to be able to use that filter. So that kind of gives you an idea of what you need to keep track of. So that's if you're using these filters visually. Now, if you're planning to do imaging, it's a bit of a different story. Because there really isn't a need to use a color filter if you're going to take an image of a planet or the moon. It's way more effective to use image processing after the fact to pull out contrast or to accentuate colors. It's way more effective than fiddling around with color filters. The main concern that we have while imaging is the atmospheric seeing. Now, filters can be used to help you with the seeing, producing sharper and better focused images. At a minimum, I recommend that you use a UV IR cut filter. This blocks the parts of the spectrum that visually you can't see anyway, and in all likelihood your telescope doesn't do a very good job of focusing. So by getting rid of those parts of the spectrum, it will help to improve the focus and the sharpness of your images. Now, if you want to push that even further, there is another alternative, and that's to use a filter that only allows light in the long wavelength end of the spectrum. So a red filter or a near infrared filter. And these do a really good job at steadying the scene. The only problem is you get a monochrome image. So if someone like me who does a lot of imaging of the moon, that's fine. But if you're imaging Jupiter or Mars, maybe it's not really going to give you the result that you want. Now, like I mentioned, for visual observing, there is a one-size-fits-all sort of filter as well for imaging. And it is, again, that moon and sky glow filter. It does a really good job of improving the contrast between different colors. So, for example, on Jupiter, we have the belts, different colors from each other, and the shrinking great red spot, all kind of different colors. Those color differences are enhanced by this filter. And I use specifically the Bader Planetarium version, it's a German company, because they have a UV IR cut filter rolled in, all into one filter. So that's my favorite filter for when I'm imaging planets. So now let's change gears and talk about deep sky. The main issue with observing deep sky objects, as we all know, is light unfortunately, this problem is getting worse every day. There are a number of different sources of light pollution that we have to deal with. Some are natural, some are man-made. In the figure here on the left, I'm going to try to illustrate for you what the main sources of light pollution are that we have to deal with. The largest source, and perhaps the one that we have the most control over, is local, direct, man-made light. Maybe, can you see that down in the corner there? So this would be light coming from the street lights on your street, or your neighbor's porch light, that sort of thing. Next is the man-made light that we see from the larger surroundings of where we live, scattered off of dust and moisture in the atmosphere over top of you. It's still fairly low altitude, but it tends to cover the whole sky from your perspective. It's what we refer to as a light dome that we see around urban centers. After that, the next source is naturally occurring sky glow, which is coming from way up at the top of our atmosphere and is due to UV rays from the sun energizing molecules at the top of our atmosphere, mostly oxygen atoms, energizing them during the day, and then at night that energy is being released as light, and we can see that light. And finally, the last source of naturally occurring light pollution is, of course, the moon. When the moon is in the sky, I think we would all agree it has a pretty big impact on what we can see with our telescope. Now, when we look at our deep sky object, like the galaxy up in the corner there, we're actually looking through all of these layers of light. All these things are adding together with the light from the object before it gets to our eye or to our camera. To give you sort of a better idea of what we're dealing with here, this graph on the right gives us a little bit more information about what the characteristics of each of these different light sources are. So the kind of typical or historical man-made light is a combination of both broadband light, so this is the blue curve here. See, there's kind of a broad spectrum emission on top of these individual spikes of emission. So these spikes are coming from high-pressure sodium lights, high-pressure mercury lights, those types of light fixtures. Now, more recently, we've seen an influx of LED-based lights. For example, I think most of the street lights in Ottawa now have been replaced with LED lights, at least in my neighborhood they are. So this magenta curve here is what a typical spectrum of an LED light fixture looks like. And it's two emission bands. A wider ones are centered on green-yellow part of the spectrum, and another one, a very narrow one, way down deep in the blue part of the spectrum. Now, sky glow, it's mostly discrete emission bands coming from different molecules in the atmosphere. The main one being molecules made from oxygen, whether it's oxygen by itself or oxygen-hydrogen radicals, some combination of that. And it's mostly discrete emissions. You can see that the red lines here, that's the sky glow. And as you get into the near infrared, the strength of that emission gets bigger. And finally, the moon is essentially a big mirror, reflecting back at us the same spectrum as the sun is emitting. So it's essentially a big broadband emitter as well. That's, again, you're way up in the infrared where you start to see some self-emission. So this is what we have to contend with. Now, what is it that we're trying to see through all this murk? Well, let's have a look. So these are some emission plots for some common deep sky objects. There are two main types of objects based on the nature of their emission spectrum. Any object that we see, because of light being given off by stars, is considered to be a broad spectrum emitter. This includes reflection nebulae, globular clusters, open clusters, and galaxies. Objects that we see because of energized gas, like hydrogen or oxygen, they're considered to be narrowband emitters. Examples of this group include H2-rich star-formed regions, or planetary nebulae, or supernova remnants. And I've given some examples of each of those here. So you can see the reference star here, Vega. This is M45. The reflection nebula that's around the Pleiades that you can't really see naked eye. And then this hump here is a typical emission spectra from a galaxy, in this case M51. So they're all broadband. There's light being given off over the whole visible spectrum. In contrast to that, nebulae like the blue lines are for NGC 7000, that's the North American nebula. It's a hydrogen-rich region. You see very characteristic spikes at hydrogen beta and hydrogen alpha. And then if a brighter nebula, by bright I mean easier to see with the naked eye, would be a planetary nebula like the Dumbbell Nebula, which has a lot more oxygen-3 emission, which we can see with our eyes at night. So that sort of gives you an idea of the two main types of deep sky objects. Now, whether or not we're trying to observe a broad spectrum object or a narrow spectrum object has a very big impact on how effective filters can be at improving our views when in light polluted conditions. Now, to make the seriousness of this light pollution problem even more evident, consider this plot here, which presents the brightness of all these different sources that I've been talking about, but plotted on the same intensity scale. So these are physical units of brightness on the left-hand side. And note that I have to use a logarithmic scale to capture the huge variation in brightness that we're talking about. So the shades of gray up here are all the different sky conditions, starting with a dark sky down here. This is a normal sky with man-made light. Then the one above it is light pollution by adding local LED streetlights. And then dark sky with the moon is like it jumps way up here. And then light pollution with full moon is way up here. And then, unfortunately, the objects we're trying to see are way down the bottom, several orders of magnitude lower brightness. Now, as a rough rule of thumb, to be able to detect something, a human, to be able to detect something visually, you need a contrast level of at least 50 to 1. So if we take as an example the galaxy M51, the blue line, under dark skies, it is about 1/10 the brightness of the sky. So it meets this criteria of detection. You could probably see M51 quite well in the dark sky. Now, if you're trying to do that from, say, my backyard in Ottawa, right now, because of the local LED lights, it's more than 10 times brighter sky brightness. So, unfortunately, there's no way that I can see this object from my backyard. There's just too much light in the sky for me to be able to detect it. The only things that can be detected under light polluted conditions are objects that have really high surface brightness. So, for example, M27, you can see these big spikes here. It is just bright enough to get that 50 to 1 ratio that we need to be able to detect it. And all these other things, forget it. You cannot see them under light polluted conditions unless we use a light pollution filter. So, it's got a big problem that we need to deal with. How do I choose the right filter for the job? Well, it's not that easy. Just like with observing the planets, our objective is to increase the contrast of the thing we're trying to see by removing what we don't want to see, which in this case is the light pollution. The additional light being added to the scene coming from the light pollution. Now, the best tool for that is a filter. It is made from using interference technology or reflective type. If you remember last month, I talked about absorptive and reflective types. The reflective type filters are the best for this application. The reason being they can be designed to have very precise cutoff wavelengths and very narrow band passes. So you can tune the filter to show you exactly what you want to see. The best filter of this category to use, it depends on a number of different things. Depends on what kind of object you're trying to see. Is it a galaxy? Is it a cluster? Is it a nebula? It also depends on the type and amount of light pollution you have. Depends on the size and type of telescope you're using. And it depends on the tracking capability of your mount if you're doing imaging. All these things play a role in what filter is best for your setup. Now, to help better understand what the choices are of filters out there, I've divided all of them up into 4 main categories. The first category is called broadband. This transmission plot shows a few examples from this category. You'll also note I've added a few vertical lines to help us to interpret the data. There are lines for things we want to see. So up here, hydrogen beta, oxygen 3. This is emission from comets, but we won't worry about that for now. Hydrogen alpha, nitrogen 2, and sulfur 2. And there's also lines for things we don't want to see. So these are mercury vapor light emission bands, mercury, we have some sodium light emission bands, and sky glow bands shown in here. So we want to see this stuff, and we don't want to see this stuff. So broadband filter is defined by this large pass band around hydrogen beta, oxygen 3, this big band here. That's what they're characterized by. Now, most of these filters are made for visual use. And so many of them don't have any response to hydrogen alpha. As you can see, the yellow filter there doesn't really have appreciable response to hydrogen alpha, but some of the other ones, they do. It's just kind of, some do, some don't. Now, the broadband category can be further subdivided based on the width of this band. And this is a system that I've come up with. I've pulled this all out of my butt, so if you look for this in a book, you're not going to find it. So I've subdivided it up in 4 subcategories. Extra wide, I would say, is any filter where the passband is bigger than 70 nanometers. And that red line there is definitely wider than 70 nanometers. These filters have luminous transmissivity or percent LT values ranging from 62 to 73%. So they pass a fair amount of the light that's coming through. White filters are in the 50 to 70 nanometer range and have a percent LT around 45 to 62%, so a little bit darker. Medium broadband filters are 35 to 50 nanometers wide. Percent LTs in the 30 to 45% range. And then finally, narrow broadband filters are in the 20 to 35 nanometer wide range and have percent LTs around 20 to 30%. Now, what is convenient about having this whole range of different subcategories is that there's going to be a filter out there somewhere that is suited for your aperture of scope. whether you have a big scope or a small scope, you're going to be able to find something that is well suited to your application. So the second category now is called narrowband. So not narrow broadband, just narrowband. Now these filters focus on a single wavelength of light at a time. The most common being hydrogen beta, oxygen 3, and hydrogen alpha. Now hydrogen alpha is really only of interest if you're doing video astronomy or imaging, because the human eye can't see that wavelength when the eyes are dark adapted. Nitrogen 2 and sulfur 2 similarly are also of interest, but only to astrophotographers, because the emissions of those wavelengths are so faint that you need to use relatively long exposure times to pick them up. Narrowband filters are available in a range of bandwidths. Those meant for visual use have bandwidths in the 10 to 20 nanometer range, and percent LT is about 10 to 20%, so quite a bit dimmer than broadband filters. And those meant for imaging alone have bandwidths less than 10 nanometers wide. The third category is called multiband. These filters are characterized by 4 or more passbands of varying bandwidth. The design philosophy of these filters is not to pass the desired wavelengths, but to block specifically light pollution wavelengths. So when you look at the plot, you can see how the dips in the curve align quite well with where I put undesired wavelengths, the mercury vapor and the sodium vapor. So that's how these filters are designed. Now, because of the broad spectrum response, there's still a lot of light getting through this filter. They provide the best white balance of any LP filter out there, which is why many people who do one-shot color imaging, like with a DSLR, for example, really like these filters, because they get a nice, well-balanced color image. Unfortunately, the broad passbands mean that these filters are rather poor at blocking light pollution overall. Broadband sources, like if the moon is up or if you have LED lights in your neighborhood, they have a big impact on how well these filters work. They greatly reduce their efficiency. Now, if you did want to use these filters visually, they range percent LT values in the 50 to 75% range. So they pass quite a large percentage of the light going through them. So the fourth and final category is new. You heard it first, folks. It's called multi-narrowband. I call it multi-narrowband. Nobody else does. Vendors of this type of filter also call it dual band or tri-band or quad band, depending on how many pass bands the filter has. The idea is to give us the performance that you would get from a narrowband filter, but for multiple wavelengths at the same time. Although they've been around for about 6 years, they really have only started to become popular because of astrophotographers who have been using them to do narrowband imaging with a color camera and getting all 3 or 2, as the case may be, of the desired wavelengths at the same time in one image, instead of taking an image with a separate filter for each wavelength. So that has made them very popular with astrophotographers, mostly people who use DSLRs. Now, these filters can also be used visually if you want. I've tried it visually, and they do work well. They have percent LT values ranging from 8 to 34%, so kind of in the darker end of the spectrum. In the transmissivity plot I've showed here, I've also included what we could call a poor man's multi-narrowband filter. That's the red curve. Whoops. All right, back here. if you look at the red curve here, there we go. Band here and a band here, but it's quite a bit wider than the other two examples given. So this is actually a medium broadband filter stacked with a UV-IR cut filter, giving us sort of a wider version of the multi-narrowband filter. And a couple of us here have used this. Simon has used this combination before, and it is quite effective at reducing light pollution. And in fact, adding a UV-IR cut filter to any broadband filter can greatly improve its performance, and talk a bit about that later. So now we have an idea of sort of the spectrum of light pollution filters that are available. This kind of captures all of the different types that you can find out there in the marketplace. But I'm sure that a lot of you probably still don't really have a good idea of how to choose a filter. So I've summarized everything that I've learned over the years into an easy-to-read table. And I'll take you through it cell by cell here. So if your target is an emission-type nebula, so planetary nebula, H2 region, or a supernova remnant, regardless of your light pollution level, it could be dark sky, it could be in the middle of the city, I recommend that you use the narrowest light pollution filter that your telescope or mount tracking will allow. And I'll talk more about that in the next slide. In the case of video or imaging, it would be the mount tracking. As I also mentioned, adding a UV or IR cut filter to an LP filter can further improve the performance of that filter in reducing light pollution. Now, if your target is a broadband object like a galaxy or a cluster, and you are under dark skies, then you should not use a filter at all. If you're using a camera, well, adding a UV IR cut will help, but a little bit, not very much, and probably not worth your time. But if you want to try it, it does help a little bit. Now, if you're looking at a broadband target like a galaxy or cluster, under light polluted skies, visually, you're out of luck. Unfortunately, there isn't really a filter out there that will help you to visually see more contrast in a galaxy or a reflection nebula. There are some vendors out there who say that their filters do help. There's even one called Galaxy Filter, and the reality is that it's just marketing hype. They don't actually do anything appreciable to improve the view. Now, if you are using a camera, whether it's a video camera or an imaging camera, to look at a galaxy or a reflection nebula, etc., then a filter can help. And your best bet is to use a filter that has pretty good response to infrared and is also sort of in the medium to wide broadband range. The IR is important because stars give off a lot of infrared, but there's not a lot of man-made light pollution in the infrared part of the spectrum. Most of it's in the visual band, it makes sense. So using a filter that passes infrared for the camera can really help to improve contrast on a galaxy. Now, one final suggestion I have is for people who are using optics that are achromatic, camera lenses, achromatic scopes, that sort of thing. You may find that some of these optics do not do a good job of focusing infrared light along with the rest of the visible spectrum. And the result is you get really fuzzy halos around stars. Adding a UV IR cut filter can help to eliminate this problem. So, as I mentioned, on the topic of how narrow a filter your telescope aperture will support, shown here is a plot similar to what I showed you a little while ago for planetary observing. It is a different graph, but it's the same basic idea. So using the percent LT values that I quoted earlier for the different categories of light pollution filter, you can figure out how narrow a filter your telescope setup could handle. So for example, I believe the narrowband filters were in the 10 to 20 range, 10 to 20% LT. So down here. So that means for those narrowband filters, you need a scope that's in the 6 to 10 inch range. Fairly big scope. Now, this is all based on my own personal experience. People with different vision and different objectives to what they want to see might have a little bit different results, but this is sort of a guideline for you of how to pick an appropriate filter for your size of telescope. Oh yes. If you're using an LP filter with a camera, then you don't need to worry about this graph. You can use them with any aperture scope, even down to a 50 millimeter or a smaller aperture camera lens. You just have to compensate by increasing your exposure time. Which is a good segue into the next slide, talking about exposure time. The plot shown here is a series of data that I collected over the years doing all of my various filter experiments. The plot shows how many times longer an exposure time in just as a multiple, how much longer I could go relative to no filter at all that I could achieve using different filters. So I use acronyms here that you don't recognize, but there's DGM GCE, that's a extra wide filter. The O3, that's a narrowband filter. These are all narrowband filters up here. There's a hydrogen alpha filter. The AUHC, that's a medium band filter. So you can see as your filter gets narrower, the length of time that you are able to expose for increases. Now, I'm not saying that you have to expose longer. I'm just saying that you are able to, and by being able to expose longer, you are able to collect more data and get a better image, more detail in the image, better contrast, etc. And I'll show you some examples of what I mean a little later. Now that's specifically for nebulae. But if we're talking about galaxies, because they are broadband emitters, adding a filter will always reduce the signal from what you're trying to see. So you have to use more exposure if you're using a filter on a galaxy or reflection nebula or other broadband object. And you can see that in the two curves that I've plotted here. The red curve is my curve fit through the data for a nebula, and the blue curve, which is higher, longer time, was observing a galaxy. So this is sort of my experience, rule of thumb kind of thing of what to expect as you use narrower and narrower filters.